Hi folks, Chris McClure. We're going to continue talking about rational functions here in section 5.3. This time focusing on graphing them, which is another way of saying examining the behavior of rational functions by constructing the graphs without necessarily relying on a graphing utility. So we go through the normal process for any function, looking at any sort of intercepts where the independent variable is equal to 0, what is the function value, or for what values of x will make the function equal to 0. And also taking a look at where the vertical and horizontal and any slant / oblique asymptotes might be. So we're going to go through a number of examples here, starting off with this first one right here. So there's a sequence of steps which they've laid out in the textbook. And this sequence of steps will just take us step by step the process of analyzing the graph of this rational function. So here we've got r of x is equal to x minus 1 over x squared minus 4. The first step is to factor the numerator and denominator and find the domain of this rational function. So when the numerator is simple, but the denominator factors as x plus 2 times x minus 2. And because this fraction is reduced to lowest terms, meaning there aren't any factors common to both the numerator and denominator, that means that we can clearly see that wherever these factors in the denominator are equal to 0, namely negative 2 and positive 2, those are going to be the x values which we exclude from the domain, and then all other real numbers will be in the domain. So we could say that the domain of this rational function is all real numbers except negative 2 and positive 2. Now let's make sure that our fraction is indeed written in lowest terms. And indeed it is. We would cancel any common factors. But even if we had identified common factors, we wouldn't necessarily want to cancel them at step 1 though, but just be aware of them. But in the original function, wherever the denominator is equal to 0, we would exclude from the denominator. Now let's locate the intercepts of the graph. So x-intercepts, y-intercepts, whatever. So first of all, can we evaluate the function at x equals 0? Well, yes, because 0 is in the domain. And indeed, when you plug 0 in for x, what do you get? You get 0 minus 1 over 0 minus 4. So you get 1/4. So 1/4 is the y-intercept. Now set the fraction equal to 0. Set the function equal to 0. Solve for x. Well, look, whenever a fraction is equal to 0, that means the numerator is equal to 0, which in this case, that means x minus 1 is equal to 0. So it means x equals 1. So 1 is the one and only x-intercept. Now, remember what we did in section 5.1 in analyzing the behavior of the graph near an x-intercept? What you do is that you take that 0 value, which in this case is 1, and then replace x everywhere else except in the factor where that produced that 0, and then see what you get. So the x minus 1 is what produced that intercept, that 0. So replace x everywhere else except in the x minus 1 factor. Replace x by x minus 1, or x equals 1, I mean. So replace x by 1 everywhere else in the function. And that's what we're doing here. Now, so you have x minus 1 divided by 1 plus 2 times 1 minus 2. 1 plus 2 is 3, 1 minus 2 is negative 1. So you get negative 1/3 times x minus 1. So what we're saying is that the graph of this function will behave in a highly localized manner, approximately like this linear equation, in the neighborhood of x equals 1. Why is this important? Well, what we could see is that, look, this line, this linear equation has a slope of negative 1/3 for the line. So what we would do is we would sketch a small line segment on the x-axis at x equals 1. That line segment would have a slope of negative 1/3. So that tells us that the graph of this function will cross the x-axis at x equals 1, going from the upper left to the lower right with the slope of negative 1/3. That's nice. Now let's locate any asymptotes. Now, vertical asymptotes are gotten by taking your reduced fraction and setting the denominator equal to 0 and solving for x. And of course, when x squared minus 4 is equal to 0, that means x is plus or minus 2. So we have two vertical asymptotes. Horizontal asymptotes are basically gotten by examining the behavior of the function for large magnitude values of x. And indeed, because this is a proper rational function, the function will tend towards 0 when x goes to positive or negative infinity. So the x-axis will be the horizontal axis. Now, will this graph, the graph of this function, will that graph ever cross this horizontal asymptote? Well, it's possible for some functions, but to see whether or not the graph of this function will cross the horizontal asymptote, all you need to do is just set the function equal to 0 and solve for x. And indeed, we have our friendly x-intercept at 1. But for other cases, the horizontal asymptote may be something other than the x-intercept. So we would set the function equal to that y value and solve for x, which will give us a nice point to plot. So this is the information that we've got so far. We've got the horizontal axis as the horizontal asymptote. So the x-axis is the horizontal asymptote. The two vertical asymptotes are at -2 and +2. We've got our x-intercept with our little line segment there. We've got our y-intercept there. Our next step then is to divide the x-axis into, I would say, maybe 4 different intervals, from -infinity to -2, from -2 to 1, from 1 to 2, and from 2 to infinity, and see where the graph is, above or below the x-axis. So that's what we've done. We've split up the x-axis into those 4 intervals, and we will pick a convenient test point, like -3, for example, on the interval from -infinity to -2, and evaluate the function at -3. Now, when you plug in -3 for x, you get -3 minus 4 divided by 9 minus 4, so you get what? -4/5, which is -0.8. Now, with that negative value of the function, that means that the graph is below the x-axis on the interval from -infinity to -2. And we know that the graph is not going to cross the x-axis at all on this interval from -infinity to -2. So if at one point the graph is below the x-axis on this interval, that means it's going to stay below the x-axis for this entire interval. And we'll do that same process for the other three intervals, which I'll let you take a look at. Test point for this next interval is at 0. 0 would be right about there. And R of 0 is equal to 1/4, and which is positive, so the graph is above the x-axis here. And then likewise, we could use 3/2 for this next intercept, and we see that R is negative there. And on the interval from 2 to infinity, we can pick 3 as our test point, and R of 3 is equal to 0.4, which is also above the x-axis. Hey, and see, these 4 points are 4 points which we could plot on the graph. So let's go ahead and plot those 4 points, and you see them right there, and right there, right there. I think we're missing one in this interval. What was supposed to go in this interval from -2 to 0, -2 to 1? Oh yeah, that's this point right here. We see that that's above, and this is below. So the y-intercept will serve as that test point. Okay, analyze the behavior of the graph near the asymptotes. Now, we have two vertical asymptotes at -2 and +2. Now, let me just point something out here. Now, let's look over here to the left of -2. Like I said, because we've already found all of our x-intercepts, and in this case, it's right there at x equals 1. We know that the graph is not going to cross the x-intercept anywhere else. So for each of these intervals, if the graph is below the x-axis on that interval at any one location, it's going to stay. The whole thing is going to be over under the x-intercept, x-axis. I mean, so you can pretty much guarantee that the graph of this rational function is just going to go down through this point and down to infinity, like this, negative infinity, like this. Because look, the graph is either going to go up or down, but because the graph is not going to cross the x-axis there, it's the only other choice is going to go down. And then to the left, as x goes to negative infinity, we have already determined that the horizontal asymptote is 0, is the x-axis. So we know that the graph is going to go to the left and up, getting closer and closer to being horizontal as the curve approaches the x-axis. Similar discussion up here. Now, on the interval from -2 to 1, look, the graph is above the x-axis here. So I could already tell you that the graph is going to go up to positive infinity as x approaches -2 from the right. Now, as x approaches +2 from the left, because the graph is below the x-axis on the interval from 1 to 2, I could tell you that the graph is going to go to negative infinity as x approaches 2 from the left. And then to the right of x equals 2, because the graph is above the x-axis at x equals 3 and doesn't cross the x-axis again, that the graph will go to positive infinity as x approaches 2 from the right. And then as x becomes infinitely positive large, infinity, going toward infinity, the graph will approach the x-axis, getting more and more horizontal. So you put all that stuff together, and then so you can draw those little arrows indicating the direction of the graph, and just go ahead and fill in all the missing parts of the curves. And this right here, folks, is the graph of this rational function. Folks, This takes about 5 or 10 minutes for each of these problems, so don't be too much in a hurry. It seems kind of complicated, but just go through that sequence of steps that we've just laid out for you. Make sure that you have read the textbook and that you know all of these steps. And it's really not hard, provided that you just take each step one at a time. Okay? Okay, folks, I'm going to take a quick break. I need to attend something. I'm going to pause this, and I'll be right back with you. Okay, back with you, folks. So here is a graph of this rational function. And let's just review the steps. So let's go back to the beginning, just to take it from the top again. Because once you understand these steps, then you can do this for any other rational function. Remember, step one is we factor the numerator and the denominator and identified any values of x in the denominator which will make the denominator equal to 0. And so we could write our domain, then cancel any common factors. So we'll have r as a reduced fraction, and we locate any intercepts, any x-intercepts and y-intercepts, and we located any vertical and horizontal intercepts, or oblique asymptotes. I should say asymptotes, not intercepts. We've already done intercepts. So vertical asymptotes and horizontal asymptotes. Or if the numerator is 1 degree higher than the denominator, then we'll have an oblique asymptote. So locate any and all asymptotes. And go ahead and plot those. And remember the localized behavior at the roots. What we did here, remember you replace x by whatever that 0 was for each of the zeros for all the other factors except for the factor which produced that 0. So for this example, at the one and only 0 of 1, you replaced x by a 1 to get this function here, which is the function of which is linear in nature. That means that the graph is a line. That means that the graph will look just like a line, at least when you zoom in very close to where the graph crosses the x-axis at that point. So we found our asymptotes for steps 4 and 5. And then we split up the x-axis, and each of these intervals split up by or demarcated by where you have vertical asymptotes and intercepts, or in any other values of x which could indicate a change in the positivity or negativity of the function. And then you pick a convenient test point in each of these intervals. Like for this one, we split up the x-axis on these 4 intervals from -infinity to -2, -2 to 1, 1 to 2, 2 to infinity. And we pick the convenient test points of -3, 0, 3/2, and 3. And evaluate the function to see whether the function is positive or negative, and then plot those points. And then, of course, we can then decide on the behavior of the graph near the vertical and horizontal asymptotes. Then that's what we're doing at step 7. And and then we go ahead and complete the graph as the last step. All right, now you can, after you sketch the graph by hand, because after all, that's what you really should be doing, is going through those 8 steps using nothing more than just a calculator, a ruler, and a pencil. And then you can check your work using your graphing calculator. Of course, your graphing calculator should verify what it is that you just did. So this is the summary of those 8 steps. Now, There are several more examples in here. Hopefully you will forgive me if I zoom through those, because we'll be here for another hour and a half if we go in through a lot of detail for those other examples. What I would like to do is just do one more example and then let you read up on the other examples, and then we're going to kind of go toward the end of the PowerPoint after this next example so I can show you a few other things. So let's now look at this next example. We're going to follow the same 8 steps, but I'm going to kind of speed it up a little bit now that you're familiar with all the steps. So the numerator and denominator is now factored. Identify any points that we can delete from the domain. Now when the denominator is equal to 0, that means x is equal to 0, so we can eliminate 0 from the denominator, or from the domain, I mean. So here's the domain, all values of x except for x equals 0. And verify that your function is, meaning this fraction, is in lowest terms. So in other situations, if you have any common factors, then you can cancel those common factors for step 2. In which case you would just have a hole wherever you have those common factors. But so anyway, let's identify any intercepts. Now, because of the fact that x is never going to be equal to 0, there is not going to be a y-intercept for the graph of this function. Now, we're going to have x-intercepts where the numerator is equal to 0. And the numerator is equal to 0 when x is equal to plus or minus 1. So those are going to be our 2 x-intercepts. And then, of course, we can examine the local behavior of those x-intercepts. First, near -1, you replace x by -1 there and there, and you get 2 times x plus 1. And near the other x-intercept, replace x by a 1 there and there, and that works out to be 2 times x minus 1. So at both intercepts, we have slopes of 2. So we would, on the graph, plot 1 and -1 on the x-axis, and then draw a small line segment with slope 2 at each of those intercepts. Okay. All right, moving along here. Here's those x-intercepts with those intercepts of slope 2, or those line segments of slope 2. The y-axis is going to be our vertical asymptote, because when you set the denominator equal to 0 and solve for x, you get 0. So x equals 0, that's the y-axis. Y-axis will act as the vertical asymptote. So that's why you see this little dashed line right there. Now, because this rational function is not a proper fraction, we can divide the numerator by the denominator. And when you do that, you get the, x with the remainder of -1. So x minus 1 over x. So y equals x will be the oblique asymptote. So you can go ahead and sketch that line, which is the graph of y equals x. Remember, the oblique asymptotes would tell you that as x approaches infinity and or negative infinity, the graph will approach infinity or negative infinity in the positive, or in the vertical sense, along the line. So along the line that way and along the line that way. Now, for the next step, step 6, we're going to divide the x-axis into the intervals from -infinity to -1, from -infinity to 1, and from 1 to infinity. And also at 0, 0 has to be included in our division of the x-axis, because there is a vertical asymptote. So we have actually these 4 intervals that we're going to then examine whether or not the function is above the x-axis, meaning is the function positive or negative. So go ahead, and you know the drill now. We did exactly the same thing with the previous example. Pick a convenient test point on each of those 4 intervals and evaluate the function at those convenient test points and see whether the function's positive or negative. So we see here, for example, on the negative infinity to negative 1 interval, the graph is going to be below the x-axis. And you can see the results for the other 3 intervals as well. Plug those points onto the graph, and then also take a look at the behavior of the graph near those asymptotes using the same techniques that we talked about before. We know, for example, that on the interval from negative 1 to 0 that the function is positive, and that x equals 0, meaning the y-axis is a vertical asymptote. So that means that as x approaches 0 from the left, that the graph is going to go straight up to toward positive infinity. But we have the x-intercept right there at negative 1. And then on the interval from negative infinity to negative 1, the function's negative. So this tells us, because we have this oblique asymptote, that as x goes to negative infinity, that the function will go to negative infinity in the direction of this line. And of course, the more negative x becomes, the closer and closer the graph of our function will get to the line y equals x. And then kind of the same discussion over on the other side. Okay, we have our vertical asymptote or oblique asymptote, and the function is going to behave as you see it for the very same reasons that we saw over on the other side here. Okay, so then lastly, go ahead and connect all those graphs portions that we had already sketched, and voila, we've got our graph. Okay, so I'll let you look at these other examples on your own here. Make sure that you're reading the textbook, and as you go through these examples, just make sure that you understand each step. So we're just going to go ahead and just zoom forward here, and here's an example where you have a rational function where the numerator and denominator are of the same degree. So you're going to have a horizontal asymptote of 3 in this case. So you're looking for intercepts and asymptotes. Essentially, that's really the big things that you're looking for. And then the behavior of the functions near your asymptotes and near your intercepts. There you're dividing up the x-axis, examining whether the graph is going to be above or below the x-axis, and so forth, and then the behavior of the function near the asymptotes, and so forth. So I'll let you look all that over on your own, and then put everything together, sketch your graph. Here's another example here, where you can just, after you have already sketched the graph, then put it in your graphing calculator and see if you can make it look like this. Either one of these, either in connected mode or dot mode. By the way, if you just go into your mode menu in your graphing calculator, you can select either connected mode or dot mode. And of course, wherever you see that there's a local minimum or local maximum value of a function, you can use the minimum or maximum function in the calculate menu to find out the exact coordinates of that minimum or maximum. And yet another example here of analyzing a rational function. Here there was that common factor of x minus 2. Now the function itself is not defined at x equals 2. But there's not going to be a vertical asymptote at x equals 2 because of the fact that you can cancel those factors. And the graph of r of x is going to look just like the graph of the 2x minus 1 over x plus 2 after you cancel the common factor of x minus 2. The only difference between the two graphs, and let me go ahead and go forward here, after you've already gone through the analysis using all those steps, the only difference in the graphs between those two functions after you've canceled x minus 2 is that the graph of r of x there is going to be missing a point at 2. So you're going to want to make sure that when you sketch this by hand that you just annotate that hole at x equals 2. Okay? Now, let's take a look at this next example here where we're going to actually kind of work backwards here. Kind of an interesting problem. Suppose that we were handed this graph here, but we don't know what the function is. And suppose that we need to come up with a rational function that this could be the graph of. So notice a couple of things. Notice that we've got x-intercepts at -2 and at +5. That at the x-intercept of -2, that the function just touches, that the graph just touches. So that means that 0 of -2 is going to have multiplicity of 2 or more. Sorry, it's going to have even multiplicity because the graph doesn't cross, it just touches. So x minus -2 squared, in other words, x plus 2 squared, would be a candidate factor in the numerator. And because the graph crosses at the x-intercept of 5, that means that x minus 5, or x minus 5 cubed, with 5 having an odd multiplicity, you could either go with 1 or 3 or whatever, but let's just go with x minus 5. Okay, so that's the numerator so far. Remember, the numerator is what determines your intercepts. Now, what determines your vertical asymptotes will be your denominator. Well, we see that we have a vertical asymptote at -5 and also at 2. Now, looking at the behavior of the graph near each of these asymptotes, we see that at x equals -5, that coming from the left, the graph goes to positive infinity, but coming from the right, the graph goes to negative infinity. So that means that in the denominator, q of x here, that x minus -5, in other words, x plus 5, will have an odd multiplicity, an odd power. But for the vertical asymptote at x equals 2, you see that as x approaches 2 from the right and from the left, that the function will go to, meaning the graph will go to negative infinity. They both, well, that the graph goes in the same direction coming from both directions. So that means that, so x plus 5 for this one here, and x minus 2 squared for this one. So because when the graph goes in the same direction as you let x approach that that value, both from the right and from the left, hold on, that means that the multiplicity on 2 is either going to be a 2 or a 4 or some other even power. So we'll just go with 2. as the multiplicity on x minus 2. So we'll try x plus 5 times x minus 2 squared in the denominator for q of x. So far this is what we have for a rational function based on the intercepts for the numerator and the vertical asymptotes for the denominator. A couple other things that we need to look at. We have a y-intercept of -2, and we also have a horizontal asymptote of 2. Now, so far, for r of x, we've got a third-degree polynomial over a third-degree polynomial, and if you multiply each of the numerator and denominator out, you'll have leading terms of x cubed. But because for long-term behavior, in the behavior of the function, that the horizontal asymptote will be y equals whatever the ratio of the leading coefficients would be, that means that we need to have a 2 in the numerator to compensate. And then the last thing that we need is to make sure that when x is equal to 0, that y is equal to -2, because if it's not, then we need to adjust somehow. But with this function now as it is, when we replace x by 0, what do we have? We've got 2 times 2 squared is 8 times -5, which is -40. Over, what, 5 times 4, which is -20. So you have -40 over -20, which is negative. Well, hold on here. No, that the denominator is going to be positive 20. So you have -40 over positive 20, which is -2. So we don't need to do any more adjustments. So we've got our y-intercepts, our x-intercepts all accounted for. We've got our vertical asymptotes and our horizontal asymptotes. So you kind of have seen the process now. If you're given the graph with all of its asymptotes and intercepts, then you can build it. You could build the function which would match that graph. Let's do an example, an application problem that uses a rational sort of function. So what we're going to do here is we are going to construct a metal can that's going to hold some product. A can in the form of a cylinder. And now we need for this metal can to have a capacity of 500 cubic centimeters, which is the same as 1 cubic liter. Now we know what a can looks like. Let's go ahead and take a look at it. Here's what our can's going to look like. Cylindrical can's going to have a certain radius and a certain height. We're told that the top and the bottom of the can are made of a special aluminum alloy that costs 0.05 cents per square centimeter. And that the sides of the can are made of a material that costs 0.02 cents per square centimeter. Now, the big reason why you want a specialized metal to be used for the top and the bottom is so as to resist corrosion. So this is all the information that you've got right here. So what we want to do is, first of all, express the cost of the material for the can as a function of the radius r of the can. That's no problem. And then graph the this function, cost as a function of r. And what will the radius have to be in order to minimize the cost, and what is that minimum cost? So I'm going to answer all those questions. The hard part, of course, is writing the function. So let's write a function first. that will tell us the cost. And then, of course, we can get the cost where the only variable that you see is going to be r, as in the radius of the can. You see right now that there's two variables, h and r. But there are actually two equations that we can write. One equation is for the cost. We have the cost, c is equal to, now, right here, pi r squared, that's the area of a circle of radius r, and there's, that'll give us the area of the top and the bottom. So you multiply it by 2 times pi r squared, that'll give you the total area of the top and the bottom. And then for the lateral surface, look, if you were to just slit the can heightways or lengthways, whatever you want to call it, and then roll it out, then look, you got a rectangle. Height h, and then remember that the circumference of a circle is 2 times pi times r, and 2 pi r will be actually the length of that rectangle. So 2 pi r h is going to be the area for the lateral surface. So 2 pi r h times 0.02 will be the cost for the material to produce the side area. So let's just go through this again. Here we've got cost is going to be the total area of the top and bottom times 0.05, because after all, the material for the top and bottom is going to be the 0.05 cents per square centimeter. And plus, here's the cost for the side as well. The area of the side times its cost. So put all that together and simplify. Now 2 times pi times 0.05. Well, 2 times 0.05 is 0.1, so you got 0.1 times pi times r squared. That's for the top and the bottom pieces. And then for the side pieces, 2 times pi times 0.02. Well, 2 times 0.02 is 0.04, so you got 0.04 times pi times h times r times h. Okay, so let's now look at another equation, this time involving the volume. Now the volume of a cylinder is pi times radius squared times h. And we have the constraint is that the volume needs to be 500, as in 500 cubic centimeters. So you set the volume equal to 500, and then you can eliminate the h variable by taking this equation, solving for h, and h will be 500 over pi r squared, and then plug this expression back into your cost function. So where you see h, replace h by 500 over pi r squared in the cost function. There it is. Simplify algebraically. Notice that pi's will cancel in the second term here. R over r squared. Well, we know that r, it doesn't make sense for r to be negative, so we can cancel r's. And 500 times 0.04 is 20. So now you've got this expression after you simplify, and if you would like to get a common denominator of r, you can multiply this first term by r over r, and when you get that and add the two fractions, this is what you get here. And lo and behold, your cost function is now only a function of r. You had to use a constraint function from the volume having to be a specific value. Then let's go ahead and find the graph, plot the graph of this cost function. Hold on. Here's the graph of that cost function. So we plotted in our graphing calculator. And then you can use your minimum function on your graphing calculator to find the coordinates of that minimum value. And when you do that, it turns out that the x coordinate, and here x is the same as r, really, that radius would have to be about 3.1692012 centimeters for a volume of 9.4661027 cubic centimeters. Actually, y is cost, isn't it? So y would actually be in terms of cents, huh? So 9.47 cents, I guess, with a radius of 3.17 centimeters. Okay? So that's how you do it. And then what would be that volume? That volume would be pi times the radius squared. The radius is 3.17. So pi times 3.17 squared times the height. Now, what would that height have to be? So you can just plug in 3.17 for r in this equation here. Square it times pi, and take 500, divide by that, and then you can plug in that value for h. Okay? Actually, the volume would be 500, wouldn't it be? So that's true, because that was a constraint. So now you know the volume. You can calculate the lateral surface area because you can solve for h. And you know what r is. R is 3.17. But what was it we were supposed to do? We were supposed to find the minimum cost, huh? So once you were able to write the cost as a function of r, and then you can just go through either algebraically, which you probably don't know how to algebraically find the minimum value, but using your graphing calculator, you can use the minimization function to find the minimum value. When you get to calculus, folks, if you're going to go on to take calculus, I will show you a technique for finding the coordinates analytically of that minimum value. So, but this time we just use graphing calculator to find that minimum radius and that minimum cost, corresponding cost. Okay? So that's it for this section. So we're going to do section 5.4 tomorrow. And so today's Tuesday, that means tomorrow is Wednesday. And on Thursday, I'm planning to do 2 sections to finish up Chapter 5 and then post the Chapter 5 quiz. And then the plan for the rest of the semester, which we only have a couple weeks, is for us to get through Chapter 6 and then maybe a few sections after that and call it good. All right, so that's it for today, and I will see you tomorrow.